In this video, we're going to be learning about something called enthalpies of formation, which will expand upon your knowledge of Hess's law. On the surface, this looks like a normal Hess's law problem, but if we look at the reactants of all three of the elementary processes, we can see a couple of things. Number one, the reactants contain only elements, and the products are exclusively compounds. So all of these are synthesis reactions. If we look at the states of matter of all of the reactants as well, we see that all of them exist in what we call the standard states of matter. Now, what this means is that the state of matter of all of the elements is the most common one, or the normal state of matter that we associate. Oxygen exists as diatomic oxygen gas and not as a solid or liquid, and calcium and carbon, which are normally on Earth solid and liquid, exist in their solid and liquid forms in this reaction. We will expand a little bit more on what enthalpies of formation are, but first let's actually go about solving this reaction, reviewing Hess's law in the process. If we look at the products of our overall reaction, we see that they match the products of steps 2 and 3, and that the quantities, one of each, also match as well. What this means is that the delta H values for step 2 and 3 can probably be left as is. This is not the case for step 1. We can see that calcium carbonate is a reactant in the overall and a product in step 1, which means we need to flip step 1, which would take a reaction that is normally exothermic and change not the magnitude of the delta H value, but the direction, to reflect that it is now an endothermic reaction, which we can represent by multiplying step 1 by -1. Before we add our delta H values together, let's rewrite equation number 1, and what we're going to do is double check that all of the products and reactants that do not appear in the final reaction get canceled when we add all three of our elementary processes together. We can see that calcium is a product in step 1 and a reactant in step 2, so it cancels, likewise with carbon, and we can do a little bit of trickery with oxygen in order to show that it cancels. We know that 1 oxygen is the same as 2/2 oxygen, and 2/2 plus 1/2 is the same thing as 3/2, meaning that oxygen cancels as well, meaning that what we are left with is calcium carbonate in the reactants and calcium oxide and carbon dioxide in the products, which is exactly our overall reaction. That means that we are now okay to add all of our delta H values together. So if you add the delta H values of all three of the elementary processes after the appropriate modification, you will find that your total delta H value comes to 178.3 kilojoules per mole. What we are interested in is the fact that the elementary processes were written in this form, in which we only have elements in their standard states. These particular elementary processes are what we call enthalpy of formation reactions, and the name pretty much tells you exactly the nature of an enthalpy of formation reaction. Formation is simply another word for synthesis. So if we look at all of these reactions, we're taking an A plus B goes to AB reaction, or A plus B plus C goes to ABC in the case of calcium carbonate. So all of these are synthesis reactions that use only elements as the reactants, and every single one of the elements exist in what we call the standard state of matter. Now, we're not just going to leave standard states as being the most normal or the most common form of each element. That's not scientific enough. So we define standard states as the state of matter of the element at what we call standard atmospheric temperature and pressure, SATP, which we define as 25 degrees Celsius or 298 degrees Kelvin on the Kelvin scale, and 101.3 kilopascals, more commonly known as 1 atmosphere or atmospheric pressure. These are the most normal conditions on Earth where human life exists. If we break these down for each of the different states of matter with gases, gases in their standard state exist as pure gases that they take at 25 degrees Celsius and in their most common elemental form. This means that oxygen, being a diatomic gas, exists as O2, whereas non-diatomic gases, like all of the noble gases like neon, exist as monoatomic gases because that is their natural form. With certain solids and liquids that actually have multiple forms that exist at 25 degrees Celsius, and these forms are what we call allotropes. The most common allotrope is the standard state. So the best example of different types of allotropes exists with carbon. The more common allotrope of carbon is the form that you find in your pencils, which is what we call graphite. I'm guessing that not too many people have pencils that are made out of diamond, because diamond is a significantly less common form of carbon, requiring a very high temperature and pressure and probably thousands to hundreds of thousands of years to create. So for that reason, graphite is the more common allotrope and therefore defined as carbon standard state. In the case of aqueous compounds or aqueous elements, the standard state always assumes that the concentration is exactly 1 mole per liter. When all of these conditions are met, we can come up with a delta H value for enthalpies of formation reactions, which is what we define as the standard molar enthalpy change. Standard molar enthalpy changes of enthalpy of formation reactions are always given a modified delta H symbol. Delta H not in the superscript or a degree sign indicates that we are dealing with standard state conditions, and the subscript F indicates that it is a formation reaction, being a synthesis reaction using only the elements that make up the compound as reactants. And we can see 2 examples of a standard molar enthalpy of formation reaction here with the matching delta H symbol that corresponds to that. So if we break both silver oxide and nitric acid down to their formation elements, we know that the standard form of silver is simply silver metal, and we know that oxygen exists as a diatomic gas. And if we balance this reaction, we can write our overall enthalpy of formation reaction. Nitric acid is a little bit more complicated because, again, it has 3 constituent elements, and all 3 of them are diatomic gases: hydrogen gas, nitrogen gas, and oxygen gas. But as long as we remember that all 3 of these gases are the diatomic form, it remains the same in terms of constructing this reaction. A little bit more tricky to balance, but now that we've done this, there is our enthalpy of formation reaction for nitric acid. So the final summarization of constructing enthalpy of formation reactions is that when you write enthalpy of formation reactions of compounds, the reaction consists of the constituent elements that make up that compound in their standard state of matter that exists at standard atmospheric temperature, let's rewrite that, temperature and pressure being 25 degrees Celsius and atmospheric pressure. Now, one common question is, what about the elements themselves? What is the enthalpy of formation for oxygen gas or silver metal? Well, remember that the standard state assumes that this is the form that all elements start in. We're not dealing with the creation of elements from fusion reactions here. That's the domain of nuclear chemistry. So the assumption is that the standard state of all of the elements is the form in which they exist naturally, meaning that they effectively on Earth have always been there as long as we have been there, and therefore the enthalpies of formation of elements in their standard form is assumed to be zero, because again, we're assuming that they have always been that way. In the next video, we're going to look at how standard molar enthalpy change and enthalpies of formation can be used to calculate the actual delta H of chemical reactions without needing to bother with the Hess's law modifications that we see here.